Welcome back to the deep dive. Today, we're doing something a little bit different. Usually we take a specific article, right? A news event, a trending topic, and we pick it apart. But today, we are tackling a landscape.
It really is a landscape. I mean, it's a territory that everyone is walking through right now, whether they realize it or not. But, very few people actually have a map.
Exactly. I feel like every single time I open my browser or check LinkedIn or heck, even just watch the evening news, I get hit with this absolute wall of buzzwords. You know the
I
one
know them.
AI, machine learning, deep learning, generative AI, LLMs, neural networks. I mean, it is just endless.
The fog, a thick fog.
It is a fog. And it feels like if you don't know the difference between, say, a random forest and a neural network, or if you can't articulate what a transformer actually does, you're somehow falling behind. It's almost anxiety-inducing.
And the problem with that fog, the real danger, is that it makes everything look like magic. It really does. When you don't understand the mechanism, it's all just AI. You sprinkle some AI dust on a business problem and cross your fingers and hope it makes money.
Right.
But that's not how any of this works. These are tools, very specific tools for very specific jobs. I mean, you wouldn't use a hammer to cut a steak, right? And you probably shouldn't be using a large language model to predict quarterly earnings.
That's the magic wand syndrome. And our goal today, based on this stack of, frankly, intimidating technical notes and research papers we have here, is to put the wand away.
Yeah.
We're going to open the toolbox. We're going to build a literal map of the machine mind.
That is the mission. We want to move from it's magic to it's math, or at least it's logic. By the end of this deep dive, we want you, the listener, to be able to look at a recommendation on Netflix or a response from ChatGPT or a fraud alert from your bank and know exactly which algorithm pulled that particular rabbit out of the hat.
I love that promise. And just to frame this for everyone listening, whether you're a developer thinking about pivoting into data science or you're a manager prepping for a high-stakes tech meeting where you really don't want to sound clueless.
We've all been there.
Or maybe you're just someone who's insanely curious about how your phone knows what you want to type before you even do it. This is for you. We are stripping away the hype.
We're going to look at the hierarchy, the machine learning hierarchy.
Okay, so where do we start? Where do we place that first big pin on this map? What's the prime meridian of this world?
The most fundamental divide, the absolute first question you have to ask in machine learning before you choose a model, before you write a single line of code is this: how is the machine learning? And there are really two main camps, supervised learning and unsupervised learning.
Okay, the core distinction. Let's unpack supervised first. I'm guessing from the name there's a teacher involved somewhere.
That is the perfect analogy. Supervised learning is a classroom. You have a teacher and you have a student, the computer model. And the defining characteristic of this classroom, the absolute key, is that the teacher has the answer key.
The answer key.
Right. So in technical terms, we call this labeled data. You don't just give the computer a math problem. You give it the problem and the solution. You show it a picture of a cat, and you literally say, this is a cat. You show it a picture of a dog, and you say, this is a dog. You do that 1,000,000 times.
It's just like flashcards for a toddler.
It is exactly like flashcards. The input is the image. The output is the label. The whole goal is that eventually, after seeing millions of these examples, you can take the answer key away. You show the student, the model, a picture it has never seen before, and based on all the patterns it learned from the flashcards, it can predict the label. It can say, that looks like a cat.
So supervised learning is all about mapping inputs to known outputs. It's about replicating a known truth.
Precisely.
Yeah.
And this is, where something like 90% of the business value in ML comes from today. Predicting customer churn, approving loans, filtering spam emails, this is all supervised learning. But there is a catch.
There's always a catch.
The catch is the answer key itself. Labeled data is expensive. Extremely expensive. A person, a human being, has to sit there and label those 1,000,000 images. Or, you need 10 years of historical stock data with the outcomes to predict next week's price. If you don't have the labels, you can't even start with supervised learning.
Which I assume leads us directly to the other side of the map, the unsupervised world.
The world without a teacher. Unsupervised learning is like throwing a detective into a room just full of evidence, but with no case file. You just dump a massive pile of raw, unlabeled data on the machine, and your only instruction is find the patterns.
So instead of saying, this is a cat, you just give it 1,000,000 animal photos and say, sort these.
Exactly. And the machine might come back and say, okay, look, I don't know what these things are called. I don't have the word cat or dog. but I have separated them into two distinct piles. Pile A seems to have pointy ears and whiskers. Pile B has floppy ears and longer snouts.
It finds the inherent structure on its own.
It hunts for the hidden structure. It's a much harder problem, obviously, but it's incredibly powerful when you don't know what you're looking for. It allows you to discover things in your data you didn't even know were there to begin with.
Okay, that is a fantastic foundation. Classroom versus detective work. Supervised versus unsupervised. Let's start in the classroom then. Let's walk through section 1, the supervised world.
Let's do it. Now, within the supervised world, we have to make one more important split right at the top. The question becomes, are we trying to predict a category, or are we trying to predict a number?
Categories versus numbers. Okay, break that down for me.
So if you're asking a yes-no question, or you're picking from a list of predefined options, that's classification. Is this email spam or not spam? Is this financial transaction fraud or legitimate? Is this picture a cat, a dog, or a bird? You're essentially putting things into different buckets.
Got it. Buckets. And the other one?
That's regression. That's when you're trying to predict a specific number, a continuous value. So what will the temperature be tomorrow? 72.5 degrees. What will the price of this house be? $452,000. It's a sliding scale, not a fixed set of buckets.
Okay, buckets versus sliding scales. That's clear. Let's start with the buckets. Classification. What's the first tool we pull out of the box? The old, rusty, reliable one.
The absolute baseline, the grandfather of them all, logistic regression.
Now stop right there. You just told me that regression is for predicting numbers, but this is called logistic regression, and you're saying it's for classification. That's just confusing branding.
It is terrible branding. It's one of the worst named things in the field. It's a historical quirk of the math because it borrows some of the mechanics from linear regression, which is for numbers. But yes, despite the name, make no mistake, logistic regression is for binary classification. Yes or no, win or loss, churn or not churn.
Okay, so terrible name aside, how does it work?
The best way to think of it is as the odds maker. A lot of people think classification models just give a hard answer, a switch, yes or no. But the real world is probabilistic, right? It's messy. Logistic regression doesn't just give you a label, it gives you a probability. It fits a very specific S-shaped curve to your data.
An S-curve.
Right, a sigmoid curve. So it doesn't just say this customer will churn, it says there's an 87% probability that this customer will churn.
And that distinction is crucial for business, isn't it? Because if a fraud model just says, this is fraud, my only option is to block the card. But if it says, there's a 60% chance this is fraud, I might just send a text message verification instead. It gives me nuance.
Exactly. It allows for risk management. It gives you a confidence score. It's simple, it's fast, and you can explain how it works to a non-technical stakeholder. If you are a data scientist starting any new project, this is your hello world. You run a logistic regression first to set a baseline. If you can solve the problem well enough with this, you stop. You don't need the fancy stuff.
All right, so that's the baseline. But what if we're dealing with words? You mentioned spam filters earlier. That feels like a different beast.
It is. And for text, especially in the early days of the internet, the undisputed king was Naive Bayes.
Naive Bayes. I love that name. Is it called naive because it's dumb?
Not dumb, just, let's say, beautifully simplistic. It's called naive because it makes a very, very strong and frankly incorrect assumption about reality. It assumes that every feature in your data, every word in an email, is completely independent of every other feature.
Give me an example of why that's naive.
Okay, imagine an email. It contains the word free, and it contains the word Viagra. Now, you and I know that free and Viagra appearing together is a gigantic red flag for spam. They are highly correlated. The combination changes the meaning entirely.
Right. Context is everything.
Naive Bayes throws context out the window. It looks at the word free and calculates the probability of spam based on that word alone. Then it looks at the word Viagra and calculates its probability of spam. It treats them as two totally separate, unrelated clues. It is completely naive to the relationship between the words.
That sounds like it would just break the model. Why would that ever work?
You would think so. And in many domains, it would fail. But mathematically, specifically for text classification, where you have thousands and thousands of words, it works shockingly well. It's the ultimate fast and dirty method. It's computationally so cheap, which is why the early email providers loved it. It could scan millions of emails in real time without, setting the server room on fire.
So it's the quantity over quality of assumptions, but the result is surprisingly decent.
That's a perfect way to put it. It's an oldie but a goodie.
Okay, moving up the sophistication ladder. I see SBM on our map here. Support vector machine. That sounds like a weapon from Star Trek. Captain, fire the support vector machine.
It does sound intense, and the math underneath it can be intense. But the core intuition behind it is beautiful. It's all geometric.
Okay, visualize it for me.
All right. Imagine you've got a sheet of paper on a table. You've scattered a bunch of red Skittles and blue Skittles on it. Your job is to take a ruler and lay it down on the paper to separate the red ones from the blue ones.
Easy enough, assuming they aren't all mixed together.
Right. But here's the SVM rule.
Yeah.
You can't just put the ruler anywhere it separates them. You have to place it so that there is the maximum possible empty space on both sides of the ruler before it touches a Skittle. You want to create the widest possible street or margin between the red village and the blue village.
Ah, so it's not just about separation, it's about the margins of safety. It's about confidence.
Exactly. That line, that ruler, it's called the hyperplane. And the few Skittles that are right on the edge of that street, the ones that are defining how wide it can be, those are the support vectors. They literally support the position of the boundary.
Okay, that makes sense for a straight line. But what if the Skittles are mixed up? What if the red ones are in a tight circle in the middle and the blue ones are in a ring all around them? You can't separate a circle from its center with a single straight ruler.
And that is where the SVM performs its magic trick. It's called the kernel trick. Imagine that sheet of paper is actually a flexible rubber sheet. The SVM algorithm metaphorically reaches under the sheet, grabs the center where the red Skittles are, and pulls it upwards, creating a 3D mountain.
Okay, so now the red Skittles are all up at the peak of the mountain, and the blue Skittles are down in the valley surrounding it.
Exactly. And now you can take a flat sheet of plexiglass and just slice right through the mountain horizontally. You've created a perfect separation. The SVM takes your 2D data, projects it into a higher dimension, in this case, 3D finds an easy way to slice it, and then projects that solution back down.
Wow, that is incredibly clever. It solves complex puzzles by just adding more dimensions.
It does. And for a long time, it was the gold standard for classification, especially on smaller data sets with complex nonlinear relationships. It's very powerful.
Okay, last one in this initial classification bucket, KNN, K nearest neighbors.
This is the peer pressure algorithm, or maybe the birds of a feather algorithm.
Show me your friends and I'll tell you who you are.
Literally that. That is the entire algorithm. KNN is interesting because it doesn't really learn a formula in the same way. It doesn't draw a line or a curve. It just memorizes all the data points.
It memorized the whole
training set. And when a new data point comes in, say a new customer you want to classify, the algorithm looks at the K closest existing customers in its memory.
The neighbors.
Right. So if you set K5, it finds the 5 nearest neighbors. And if, say, 4 of those neighbors are labeled defaulted on loan and only one is paid loan, the model labels the new guy as a defaulter. It's just a simple majority vote.
That sounds almost too simple. What are the downsides? Why isn't this used for everything?
2 big reasons. First, picking K is a bit of a dark art. If K is too small, like K1, you get really influenced by noise, that one weird neighbor who's nothing like the others. If K too big, you smooth everything out and lose the local details. But the real killer is scale.
Because it has to measure the distance to every single other point.
Every single one. Imagine you're in a stadium with 100,000 people. To find your 3 nearest neighbors, I had to take out a tape measure and physically measure the distance from you to every single one of those 100,000 other people. It's computationally brutal. It's great for a small dinner party, but it's terrible for a massive rave.
That's a great mental image. Okay, so that's classification. We've sorted our Skittles into buckets. Now let's talk about regression, predicting the actual numbers.
Right. And the star of the show here, the one everyone learns first, is linear regression. This is straight out of high school stats class. You have a scatter plot of points, maybe house size on the x-axis and house price on the y-axis. You just try to draw a single straight line through the middle of the points that minimizes the overall error.
The classic line of best fit.
That's the one. It's simple, it's super interpretable, and it tells you the relationship. You get a nice formula. For every extra square foot, the price goes up by, say, $100. But linear regression has a tendency to be a little bit too eager.
Eager? What do you mean?
It can overinterpret noise in the data. If you have a few weird outlier data points, the line might tilt itself dramatically just to try and accommodate them. It can be too sensitive. And this is where we introduce the cowboys, Ridge and Lasso.
The cowboys.
Now,
I like it. Explain.
Ridge and Lasso are 2 different flavors of a technique called regularization. And regularization is just a fancy word for penalty. They punish the model for being too complex or having coefficients that are too large.
Like a slap on the wrist for getting too excited about a variable.
Exactly. Lasso, in particular, is the more aggressive of the two. It's like a strict minimalist. If a variable, a feature in your data, doesn't contribute significantly to the prediction, Lasso will shrink its importance, its coefficient, all the way down to zero. It effectively performs automatic feature selection. It deletes useless variables.
So if I'm trying to predict house prices and I include a useless variable like color of the front door, Lasso might just say, nope, that doesn't matter, 0, get it out of here.
That's exactly what it does. It keeps the model honest and helps prevent overfitting, which is the cardinal sin of machine learning. That's when your model memorizes the training data perfectly, but fails spectacularly on new, real-world data.
Now we absolutely have to talk about the family of models that seems to dominate the middle ground of data science, especially for business data. The trees.
Ah, yes. The evolution of trees. This is a crucial section. If you're doing data science on tabular data, spreadsheets, Excel files, SQL tables, there's a very high chance that today you're using some form of tree-based model.
And it all starts with the single decision tree.
Which is basically just a flowchart. It's a series of if-then-else questions. Is the credit score above 700? If yes, go left. If no, go right. Is the annual income above $50K? Yes, no. You keep asking these simple questions until you end up in a final leaf node that gives you the prediction.
I love these because they are so transparent. You can literally print out the flowchart and show it to your boss and say, look, here's the exact logic for why we approved or rejected this loan.
That interpretability is their absolute superpower. But, like a single tree in a storm, they are brittle. A single decision tree can be very unstable. If you just change a few data points, the entire structure of the tree might change dramatically. It's very prone to overfitting. It learns the training data too well, including all its quirks and noise.
So how do you stabilize it? How do you make it stronger?
You don't plant one tree. You plant a forest, a random forest.
Strength in numbers.
Exactly. A random forest trains hundreds, sometimes thousands, of individual decision trees. But, and this is the critical part, it trains each tree on a slightly different, random subset of the data. And at each split in the tree, it only considers a random subset of the available questions. It intentionally makes each tree a little bit different, a little bit weaker on its own.
So you end up with a huge committee of unique, slightly different experts.
And then you let them all vote. For classification, it's a majority vote. For regression, you average their predictions. It's the wisdom of crowds in action. If one tree makes a weird mistake because it saw a strange outlier in its little sample of data, the 99 other trees will overrule it. The result is a model that is incredibly robust. It's very, very hard to break a random forest.
I've heard it's not always the most accurate, right? It's like the safest choice, but maybe not the one that wins competitions.
That's correct. If you want to squeeze out every last drop of performance, if you want to win a competition like on the platform Kaggle, you move to the next step in the evolution. Gradient boosting. Models with names like XGBoost and LightGBM.
Okay, how is boosting different from a forest? It's still a bunch of trees, isn't it?
It is, but the philosophy is completely different. In a random forest, all the trees are independent. They're built in parallel. They don't talk to each other. In gradient boosting, the trees are a team. They work sequentially, one after another.
Like a relay race.
It's a bit like that. Imagine tree #1 takes the first shot at the problem. It does its best, and maybe it gets 70% of the answers right, but it makes mistakes on the other 30%. Now, tree #2 doesn't start from scratch. Tree #2 looks only at the mistakes that tree #1 made. Its entire job is to correct those specific errors.
So it focuses on the hard problems that the first tree got wrong.
Precisely. Then tree #3 comes in and focuses on the remaining errors that tree #2 couldn't fix. Each new tree is a specialist in fixing the mistakes of the one before it. By the time you get to tree #100, you have a model that has become laser-focused on the most difficult, nuanced edge cases in the data.
So a random forest is a democracy. Everyone gets an equal vote. But gradient boosting is more like a team of specialists, each one cleaning up the mess left by the previous one.
That is a brilliant analogy, and that's why boosting models so often win competitions. They squeeze every last drop of signal out of the data. The downside is that they're harder to tune.
Oh.
If you're not careful, they can start obsessing over noise in the data and overfit badly.
High risk, high reward.
Exactly.
Okay, we have conquered the supervised world. We have our classifiers, our regressors, and our powerful forest of trees. Now, it's time to take away the answer key. We are stepping across the divide into Section 2. The unsupervised world. The detective agency is open for business.
This is where the machine has to get creative, and the most common, most fundamental task here is clustering.
simply grouping similar things together.
Right. You give the machine all your customer data, their age, their spending habits, their location, and you just say, find the natural segments in this population. And the most famous algorithm for this, the one everyone learns, is k-means.
Not to be confused with k-nearest neighbors, the names are so similar.
Totally different things. In k-means, the k is a number you have to decide beforehand. You have to tell the algorithm how many groups or clusters you're looking for. Let's say you pick k3. The algorithm then randomly drops 3 points, we call them centroids, onto your data map.
Like planting 3 different colored flags.
Yes, exactly.
Yeah.
Then every single data point look at the 3 flags and rushes to the one it's closest to. That forms your initial 3 clusters. Then the flags update their position. Each flag moves to the center of its new cluster.
Okay.
And then all the data points reshuffle, rushing to the new flag positions. Then the flags move again. It's this iterative process that repeats until the flags stop moving, until the cluster assignments are stable.
It sounds like a game of musical chairs where the chairs move.
It really is.
Yeah.
And it works very well for nice, round, well-separated blobs of data. But it has a couple of fatal flaws. First, as I said, you have to tell it K. You have to guess, find me 3 groups. But what if there are actually 5 natural groups in your data? K-means will still force everything into 3 groups. It will merge distinct groups just to satisfy your command.
So it's stubborn. And what if the groups aren't round like blobs? What if they're shaped like, I don't know, a crescent moon or a long, thin line?
K-means fails miserably there. Because it relies on simple, straight-line distance to a center point, it can't discover complex shapes. For that, we need a more sophisticated tool like dbscan.
Density-based spatial clustering of applications with noise.
Wow, that is a mouthful.
Let's just call it the contagion model. dbscan works completely differently. It doesn't look for centers. It picks a random point and looks around in a small neighborhood. If there are enough other points nearby, it says, okay, we are a core part of a cluster. Then it jumps to each of those neighbors and checks their neighbors.
So it spreads through dense regions like a virus?
Exactly. It flows through the data like water, connecting dense areas. Because of this, it can discover clusters of any arbitrary shape. You can find a winding river. It can find a ring. And crucially, what happens if a point has no neighbors? If it's all alone?
The loner. The outlier.
dbscan marks it as noise and simply ignores it, sets it aside. K-means would have been forced to cram that loner into one of its clusters. dbscan acknowledges that some points just don't belong. This makes it excellent for real-world data, which is always messy.
But I'm looking at a note here in our tech guide. dbscan is not native to PySpark. Why is that?
Right, so if you're working with big data, we're talking billions of rows distributed across a computing cluster. dbscan becomes very computationally heavy. That neighbor hopping process is very sequential and hard to do in parallel across many machines. So engineers often have to resort to approximations or different libraries to use it at scale.
We also have LDA in this clustering section.
LDA is a specialized tool specifically for text. It stands for Latent Dirichlet Allocation. The best way to think of it is as topic modeling. You can feed it a million news articles, and it will scan through them to find clusters of words that tend to appear together frequently. It might come back and say, hey, documents 1, 5, and 10 all talk about government, election, and policy. Let's call that topic A. And documents 2, 7, and 12 all use market, stock, and trade. That's topic B.
So it automatically discovers the hidden themes or topics within a huge library of documents.
Very cool.
Okay, next up in the unsupervised world, anomaly detection. Finding the needle in the haystack.
This is a huge area for things like fraud detection or finding defective parts in a manufacturing line. You want to find that one transaction, that one data point that just looks weird. And one of the coolest algorithms here is the isolation forest.
Isolation forest, so it's related to random forest.
It uses trees, but for a totally different purpose. It finds the weirdo by trying to isolate it. Imagine you have your data set plotted out. The algorithm makes a random cut through the data, then another random cut, then another.
It's just randomly slicing up the data space.
Yes. Now think about a normal data point. It's probably buried deep in the middle of a dense cluster of other points. To isolate that single point with random cuts, you'd have to make many, many cuts to shave away all of its neighbors one by one.
Okay, that makes sense. It would take a lot of work.
But an anomaly, a point that's sitting all by itself way out in the margins, you might be able to isolate it from everything else with just 1 or 2 random cuts.
Ah, so the algorithm isn't looking at the data, it's just counting the cuts. It only took me 2 cuts to isolate this point. It must be an anomaly.
That's it exactly. A short path length in the tree equals anomaly. It's incredibly clever and very efficient because you don't have to calculate complex distances, you just chop.
Elegant. I really like that. And again, I see another technical note. To run this at scale on Spark, you need a library called Synapse ML.
That's right. It's a library from Microsoft that adds a bunch of powerful ML capabilities to Spark, crucial for doing anomaly detection on massive data sets. There's also another approach using neural networks called an autoencoder.
How would a neural network find anomalies?
An autoencoder is trained to do one thing: compress data down to its essential essence and then reconstruct it back to its original form. It gets very, very good at reconstructing normal data that it has seen many times. So if you feed it something weird, an anomaly it's never seen before, it fails. It can't reconstruct it properly. The difference between the original and the reconstruction, the error, is really high, and that high error is your anomaly flag.
Okay, before we leave the unsupervised world, we have to touch on recommendations, the engine that keeps us all doom scrolling and binge watching.
The infamous Netflix algorithm. The classic approach here, and one that's still used, is ALS, which stands for alternating least squares. It's a type of matrix factorization.
Okay, unpack matrix factorization for me.
Imagine a gigantic grid, a matrix. The rows are all of your users. The columns are all of your movies. In the cells, you have the ratings that users have given to movies. But most of this grid is empty, right? You haven't rated most movies. ALS is a mathematical technique that tries to guess the numbers for all the empty spots based on the patterns in the spots that are filled in. It does this by discovering latent factors, hidden features, about both users and movies. It might learn that user A likes movies with explosions and car chases, and that movie B has a high score on the explosions and car chases factor.
So it connects them. And then there's the classic retail example that always comes up, FP growth.
The beer and diapers algorithm. It's an algorithm for frequent item set mining. It scans through millions of supermarket receipts to find associations. It's the algorithm that famously discovered that men who buy diapers on a Friday afternoon also tend to buy beer. It's all about finding those if you buy X, you are also likely to buy Y rules.
So that's the unsupervised world. No teachers, no answer keys, just finding hidden patterns. Now, we have to make a jump, a big one. We're leaving the world of nice, neat spreadsheets and tables. We're entering section 3, deep learning and the neural network families.
This is the complexity jump.
Yeah.
Up until now, we've mostly been talking about structured data, data that fits nicely into rows and columns. But what if your data is a photograph, or a snippet of audio, or a paragraph of text? This is unstructured data.
And that's where neural networks come in. And the most basic one, the starting point, is the MLP, the multi-layer perceptron.
This is the fundamental architecture. It's very loosely inspired by the structure of the human brain. You have layers of interconnected neurons. Information flows from an input layer through one or more hidden layers where all the mathematical computation happens, to an output layer that gives you the final prediction.
Our source notes mention that in a framework like PySpark, you literally have to define the structure of these layers manually. You'd write something like 4, 5, 4, 3.
That's right. You are explicitly defining the architecture. My input layer has 4 neurons, the first hidden layer has 5, the second hidden layer has 4, and my output layer has 3. It's the fundamental building block of everything else in deep learning. It's pretty good for complex classification on tabular data, but it really struggles with things like images.
Why? Because an image is just too much data for it to handle.
It's not just the amount, it's the structure. If you want to feed an image into a basic MLP, you have to flatten it. You take that 2D grid of pixels and you stretch it out into one single long vector of numbers. And when you do that, you lose all the spatial structure. You lose the fact that this pixel is next to that pixel. The model has no idea that the pixels forming an eyebrow are right above the pixels forming an eye.
So we need a specialist. If we're dealing with vision with eyes, we need a CNN.
A convolutional neural network. This architecture completely changed the world of computer vision. An MLP looks at the whole image at once and gets confused. A CNN, on the other hand, scans the image.
It scans it.
Imagine it has a small magnifying glass, or a filter. It slides this small window over every part of the image. In the first layer, it's not looking for cats or dogs. It's just looking for very simple things like vertical edges, horizontal edges, or simple color gradients. Then the next layer takes those patterns and combines them. It learns to find corners, curves, and textures. The next layer combines those to find shapes like eyes and noses. It builds up understanding hierarchically, from simple pixels to complex objects, all while preserving the spatial relationship of the parts.
Okay, so CNNs are the specialists for space, for images. But what about time? What about sequence data like audio or text?
For that, you need a different specialist. You need the RNN, or a more advanced version called an LSTM, a recurrent neural network.
And the key feature here, the big innovation, is memory, right?
Yes. A standard network, like an MLP or a CNN, has no memory of the past. If you show it a video one frame at a time, it has no idea that frame 2 came directly after frame 1. An RNN has a loop. Information from one step is fed back into the network to influence the next step. It remembers what it just saw.
Which is absolutely essential for language or music. You can't possibly understand the end of a sentence if you've already forgotten the beginning.
Exactly. If I say, the clouds are in the Merrick, you need the context of the word clouds to predict the next word, sky. Standard RNNs had a problem, though. They had very short-term memory. They'd forget the beginning of a long paragraph. That's why the LSTM, the long short-term memory network, was created. It has a more sophisticated internal structure that allows it to hold on to relevant context for much longer durations.
But even LSTMs have now been largely dethroned, haven't they? And this brings us to what might be the biggest revolution in AI in the last decade, Section 4, the Transformer Revolution.
This is the moment everything changed for natural language processing, or NLP. The transformer architecture, introduced in a 2017 paper called Attention is All You Need, it completely replaced RNNs and LSTMs because it found a much, much better way to handle context.
And why did it kill the LSTM? What was the big advantage?
LSTMs, by their very nature, are sequential. To process word number 100 in a document, they first have to process words 1 through 99 in order. It's slow, and it's very difficult to parallelize on modern hardware like GPUs. Transformers, however, allow the model to look at the entire sentence or paragraph all at once.
Parallel processing, a huge speed up.
A massive speed up, and the secret sauce that makes this possible is a mechanism called self-attention. Imagine you're at a loud cocktail party. You're trying to have a conversation with one person. Your ears are picking up all the sound in the room, but your brain is able to attend only to that one person's voice. You effectively tune out the irrelevant noise.
You focus.
Transformers do that with words. When the model is processing the word bank in the sentence, I went fishing by the riverbank, the attention mechanism looks at all the other words in the sentence. It sees fishing and river and assigns them very high attention scores. It basically ignores words like I and the. It knows that bank means the side of a river, not a financial institution, because of the context it's paying attention to.
So it uses the entire context of the sentence to define the meaning of each word, all at the same time.
All at the same time. And this incredibly powerful architecture quickly split into two main branches, two different philosophical approaches. And these are the two titans of modern NLP, BERT versus GPT.
Let's really distinguish these, because I think a lot of people use them interchangeably. Let's start with BERT.
BERT stands for Bidirectional Encoder Representations from Transformers. The most important word in that entire acronym is bidirectional.
It reads in both directions.
Exactly. Imagine you're reading a sentence, but a word is missing in the middle. The man went to the blank to deposit his money. To correctly guess the word bank, you need to read what came before it, went to the, and what came after it, to deposit his money. You need context from both directions simultaneously.
So BERT is the reader. Its job is to analyze and understand existing text.
It is the ultimate analyst. It's designed to understand meaning and context. That's why it's used for things like search engines, for classification, for sentiment analysis. When you type a messy query into Google, it's a BERT-like model that's trying to understand the true intent behind your words.
And in the new world of generative AI, BERT is the engine behind RAG retrieval augmented generation. It's the part that goes and finds the relevant facts from a database.
Exactly. It's used to create the embeddings, the mathematical representations of meaning. It turns words and sentences into numbers in a way that allows the machine to find similar concepts, which is crucial for search and memory.
Okay, so if BERT is the reader, the analyst, then GPT is
The writer, the creator. GPT stands for Generative Pre-trained Transformer, and it's a decoder-style model.
And it is unidirectional.
It only reads left to right. It works just like the autocomplete on your phone.
Yeah.
Its only job is to predict the very next word based on all the previous words it has seen. It doesn't know what the end of the sentence is going to be. It's creating it, one word at a time as it goes.
So BERT looks at the whole finished page to understand it. GPT holds the pen and writes the page from scratch.
That is a perfect analogy. And that's why GPT and similar models are used for chatbots, for text generation, for summarization. It's the creative engine.
Yeah.
When people talk about an LLM, a large language model, they're typically talking about a GPT-style decoder model.
This brings us perfectly into our next chapter, Section 5, Generative AI, the creative engine itself.
And here's the big aha moment that I think grounds all of this. Generative AI is not magic. It is not some new, fundamentally different type of intelligence. It is simply massive scale supervised learning.
Wait, really? We're back to the classroom, back to the flashcards?
In a way, yes. Think about how you train a model like GPT. You feed it billions and billions of sentences from the internet, but you hide the last word. You're giving it an input, the start of the sentence, and you have the correct answer, the next word. The model's job is to predict that word. It is a supervised task, just on an unimaginable planet-spanning scale.
That really does demystify it quite a bit. Now, we've covered text generation with GPT. Let's talk about image generation. How does a computer dream up a picture of an astronaut riding a horse on Mars in the style of Van Gogh?
There are a few different families of models here. The older ones are things like VAEs or variational autoencoders. They're good for simple generation. But the two big players that people always talk about are GANs and diffusion models.
Let's act out the GAN, the Generative Adversarial Network. It's a rivalry.
It's a duel. You have two neural networks that are locked in a fight to the death. You have the generator and the discriminator.
Okay, I'll be the generator. I'm the forger. My job is to learn how to paint a fake Picasso. I'll start by just making random noise.
And I'm the discriminator. I'm the expert art detective. You show me your first painting, the random noise, and I compare it to a real Picasso.
Yeah.
I say, that's obviously fake, not even close.
So I take that feedback, I tweak my process a little bit, and I try again. I show you a slightly better forgery.
And I look at it and say, getting warmer, but the brushstrokes are all wrong, still fake.
And we do this millions and millions of times. I get better at forging, and you get better at detecting forgeries.
Until eventually you, the generator, becomes so good at painting fake Picassos that I, the discriminator, can't tell the difference anymore. My accuracy at detecting fakes drops to 50-50, a coin flip. At that point, the generator has learned the underlying patterns of a Picasso and can create new, original ones. That's a Jan.
That is an intense process, but that's not what the big models like Midjourney or DALL-E 3 are using today, is it?
No. For the most part, they have moved on to Stable Diffusion. That is the modern standard. And the logic behind it is completely different. It's not a forgery contest. It's a denoising process.
Okay, how does denoising work?
Imagine you take a crystal clear photograph and you add a tiny, tiny little bit of static or snow to it. Then you add a little bit more and more. And you keep doing this until the original image is completely gone, and all you have left is a screen of pure gray noise.
Okay, you've completely destroyed the image.
Now, you train a powerful neural network to do the exact reverse of that process. You show it the slightly noisy image and teach it to predict the original clean image. You teach it how to subtract the noise.
So it learns to clean images.
Exactly. It becomes an expert at denoising. So now, when you give it a prompt like an astronaut, it starts with a field of pure random static. And it uses the text prompt as a guide to start seeing an astronaut in the noise. It then subtracts the noise step by step, gradually refining the image until a clear picture of an astronaut emerges.
So it's like a sculptor looking at a block of marble and chipping away everything that doesn't look like the statue.
That is a beautiful way to put it. That's diffusion.
All right, we have toured the entire map. From simple straight lines and linear regression all the way to hallucinating images out of noise with diffusion models. But now comes the most practical question. The listener is thinking, okay, I have a problem to solve at work tomorrow. Which piece of software do I actually use? This is section 6, the tool docs.
The framework selection guide, this is where the rubber meets the road. Because knowing the theory is one thing, but you need to know which library to actually import in your code.
Okay, scenario 1. I have a CSV file. It's got maybe 50,000 rows of customer data. It fits comfortably on my laptop's memory. I want to build a model to predict customer churn.
Simple. You use scikit-learn. It's the Swiss Army knife of machine learning in Python. It has almost every one of the classic models we discussed. Logistic regression, random forest, SVM, k-means, you name it. It's got a clean API, it's easy to use, and it just works. If your data fits in RAM, you always start here.
Scenario 2. I work in a massive fintech company. I have 10 billion credit card transactions. I need to build a fraud detection model. This data absolutely does not fit on my laptop.
You need a distributed computing framework. The standard here is PySpark, and its machine learning library, MLlib. This is designed to run on a cluster of dozens or hundreds of machines. Trying to load that data with scikit-learn will instantly crash your computer. PySpark is built to chew through that scale of data. It has its own distributed versions of random forest, logistic regression, and so on.
Scenario 3. I'm a competitive data scientist. I'm entering a Kaggle competition. The data is tabular. basically a big Excel sheet, and my only goal is to get the absolute maximum accuracy possible. I don't care about interpretability, I just want to win.
You are using XGBoost or LightGBM. These are the standalone, highly optimized gradient boosting libraries. They are the undisputed champions of tabular data competitions. They are faster and consistently more accurate on this type of data than the standard implementations you'd find in scikit-learn or Spark.
Scenario 4. I want to build a custom chatbot for my company or an image classifier that can identify our products. I'm doing deep learning.
Now you're in the world of the heavyweights, PyTorch or TensorFlow. PyTorch is generally favored by the research community and is known for being very flexible and Pythonic. TensorFlow is Google's ecosystem, and it's known for being very robust for production deployment. You can't go wrong with either, but these are the two main choices for building custom neural networks.
And one last niche one. I need to do that massive anomaly detection on Spark, and I specifically want to use the isolation forest algorithm.
Then you need Synapse ML. As we mentioned, standard Spark MLlib doesn't have a built-in isolation forest. If you need that specific, powerful algorithm on big data, you need to bring in that Microsoft library.
There it is, the decision matrix. The map.
We made it across the territory.
Let's just look back at the journey for a second. We started with the strict, simple rules of supervised learning the teacher and the student with the answer key. Then we explored the wild west of unsupervised learning the detective, finding hidden patterns in the dark.
We then climbed that complexity ladder up to neural networks, giving the machine specialized tools like eyes, CNNs, and memory LSTMs.
And we finished with the modern era, the transformer revolution, understanding the difference between the reader, BERT, and the writer, GPT, and finally, the almost magical creative power of generative AI.
It's a lot of ground to cover, but I really hope listeners can see the thread that runs through it all. It's not magic. It's a hierarchy of tools, and each tool is designed for a specific kind of data and a specific kind of question.
So when all is said and done, what's the final takeaway? When the listener closes this app and goes about their day, what's the one thing that should stick with them?
I think the most powerful mental shift is to stop seeing these things as a monolithic AI and start understanding the intent of the specific model. When you use a search engine, you now know you're interacting with a reader, a BERT-like model that is desperately trying to understand your query. When you talk to a chatbot, you know you're talking to a writer, a GPT model, that is just trying to predict the next most plausible word. When you see a stunning AI image, you know you're looking at the result of a denoising process.
It demystifies the ghost in the machine. It gives you a language for what's actually happening.
Exactly.
Yeah.
It changes your entire relationship with the technology. You stop asking, what does the AI think? And you start asking the much better question, what pattern is this specific model optimizing for?
Which leads us to a pretty provocative thought to end on, doesn't it?
It does. We started this last section by saying that Gen AI is just massive scale supervised learning.
Right.
We are teaching it to predict the next word, the next pixel.
Yeah.
We are essentially teaching it to mimic the vast repository of human text and images.
Right, to mimic us.
But what if these models are also using unsupervised techniques deep inside their complex layers to find hidden patterns in the data that we humans can't see, relationships that exist in 500 or 1,000 dimensions?
Yeah.
And then we combine that latent understanding with the massive scale of generative AI. The question becomes, are we just teaching them to mimic us? Or are they starting to understand a version of reality, a hidden map of the world, of logic, of language that is actually far more detailed and complex than our own?
Are they just copying our homework, or have they secretly rewritten the entire textbook in a language we don't even know how to speak yet?
That is the question.
A terrifying and incredibly exciting thought to end on. Thank you so much for walking the territory with us today.
It was my pleasure.
And to our listeners, good luck with your own maps. We'll see you in the next deep dive.